Hi guys, welcome back to Think Tank Online Learning. So in this video, I want to verify the divergence theorem. Okay, so I given a problem. Find the flux of a vector field, okay, out of a unit cube. So you should know that a cube has 6 sides, okay. And I'm given the limits for z 0 to 1, y 0 to 1, for x 0 to 1. And I want to verify the divergence theorem. Okay, so by verifying we mean want to evaluate the flux on both sides. Okay, so first of all, I've drawn this cube. Okay, so the total flux that pass out of this shape, you can just determine it using the divergence theorem, and it is very easy. All you need to do is to find the divergence of this vector field. After that, and to set up our triple integral. Okay, but since we want to verify, we want the left hand side here. Okay, so we want to find the area, the flux that passes through this face, this face, this face, this face, this face, and the face opposite to this one. Okay, so what we're going to do, first of all, I'm going to use the divergence theorem, which is very fast, and after that we evaluate the flux on each of these faces. Okay, so first of all, what I'm going to do, I'm going to find the divergence. Okay, so I'm going to say divergence of the vector function f. Okay, and divergence is just a dot product of the gradient times this vector function f. So in other words, I'm just saying I'm going to say partial x for the I component, which is xy, plus partial y for the j component, which is z y squared, plus partial z for the co-component, in this case is z to the power 3. Okay, after that we're going to differentiate. We're going to differentiate partially. Okay, so here we're going to have y, no, don't have units here, plus 2zy, okay, plus 3z squared. Okay, like that. Okay, so in this example, as you can see, our limits are very easy to identify. Okay, so we have the x limits. So x ranges from 0 to 1, then y ranges from 0 to 1. That same applies to z from 0 to 1. Okay, so our triple integral is going to be very easy. So what we're going to say is that 1 to find the triple integral. Okay, so x is my outer, 0 1, then y 0 1, then z 0 1. This divergence of this vector field, y plus 2zy plus 3z squared dz dy dx. Okay, and after that we're just integrating with respect to z. Okay, so if you integrate respect to z, what we're going to get, 1 0 1 0, and now y is just a constant, so we're going to have yz. Here we're going to have 2z squared y over 2 plus 3z to the power 3 over 3. Our limits 1 0 dy dx. Okay, and here we're going to say upper bound minus lower bound. So the upper bound is 1. Okay, to replace z with 1, then the lower bound is 0. Okay, so if we place everything 0, we're going to get 0 here. So we're going to say 1 0, and for the upper bound here, we're going to just left with y. And as you can see, 2 and 2 we cancel, 3 and 3 we cancel, so we're going to have plus y here. Okay, here, and we're going to have plus 1 dy dx. Okay, and now, so this is same as saying 1 0 1 0, 2y plus 1 dy dx. Okay, so now I want to integrate here. Okay, so if we integrate respect to y, we're going to have 1 0 2y squared over 2 plus y, our limits 1 0 dx. Okay, then this one and this one are going to get 1, and we're just saying upper bound minus lower bound, and our upper bound is 1, so we're going to have 1 0, and if say 1 plus 1, we're going to have 2 dx. And if we integrate a constant respect to x, we're going to get 2x. Our limits 1 0, so this is equal to 2. So this is the total flux that passes out through the unit cube. Okay, and now we want to verify, so that means if calculate the flux that passes through this face, each and every face of a cube, and we add the total together, we should get 2. Okay, so now I want to evaluate the flux of each and every face. Okay, so this face is now referring to them as surfaces. Okay, so the first thing I'm going to do, I am going to start with this surface. Okay, the red surface. Okay, so this is the red surface. Okay, so for the red surface we have a rectangle. Okay, so by the way, this is the z and this is y. Okay, so y is from 0 to 1, z from 0 to 1. Okay, and we want to find the area of these surfaces using double integral. Okay, so we're going to say c ranges from 0 to 1 and y ranges from 0 to 1, 0, y 0 to 1 also. Okay, then we have f, which is xyi plus z y squared j plus z to the power 3 k. Okay, now you have to multiply this by the normal. Okay, so what is the outward normal, since we're looking for the outward flux? Okay, so the outward normal, so want to find the vector that is perpendicular to this surface. So the outward, as you can see, let's say if the fluid is to flow out of this box, okay, it will come in this direction, right? So this is the normal. Okay, so the normal is in the negative, in the positive x direction. So this is the positive x direction, it will come in this direction. Okay, so that is going to be the normal. So x, the vector component for negative x, for positive x, is going to be I. Okay, and I'm going to say dz dy dz or dz dy. Okay, and if we perform our integral here, okay, so we're going to get 1 0 1 0. If we have I, so that means j component is 0 and the k component is 0, so we're going to have xy dy dz. Okay, so if we integrate here, what is the x here? Okay, so the value for x is 1 here, so we're going to have 1 0 0 1 y dy dz. Okay, so now let's integrate with respect to y first. So we're going to have 1 0 y squared over 2 from 0 to 1 dz. Okay, and what do we got? What do we get here? Okay, just have 1 0 1 half dz. Okay, and if we integrate with respect to z, because we have 1 half z from 0 to 1, and we have 1 half here. Okay, so by the way, I think the first thing I should have just written here is to tell you that the total flux. Okay, so we have main surfaces. I'm going to name this surface, I'm going to call it, okay, let me call this one surface number 1. Okay, so this is surface number 1, and we have 6 surfaces, which are, in other words, there are 6 faces. Okay, so the total flux is going to be the total flux. Okay, so the total flux here, total flux is going to be the flux of the surface 1, surface 2, plus surface 3, plus surface 4, plus surface 5, plus surface number 6. Now going to add the total flux for each and every surface, and we should get 2. So that means if we get 2, that means we verified the divergence theorem. Okay, so now we're going to surface number 2. Okay, so let me just say surface number 2 here. So for surface number 2, the order doesn't matter. I'm going to choose this surface. Okay, so the red, the green, the blue, and blue. Okay, so let me just draw a triangle here. Okay, so for this surface, you can see we have x. Okay, so this is x from 0 to 1, and this one is the height, it's z from 0 to 1. Okay, and we have said the surface number 2. So what we're going to do, we're going to integrate it using double integrals. Okay, so now we have the double integral. I'm going to say from x, and now we have, I'm going to call, okay, I forget to name this one. This one is z. Okay, this one is z. Okay, from 0 to 1, and we have our vector xyi plus z y squared j plus z to the power 3 k. Okay, and for the normal, okay, so the outward normal is in this direction. Okay, that is the outward normal, which is perpendicular to this surface. Okay, and it's in positive y direction. So the vector field, the vector notation for y is j, and it's positive, and we have dz dx. Okay, so I common is 0, k common is 0. So here we're going to have 1 0 1 0. So if you multiply, you're going to have z y to the power 2 k dz dx. Okay, so now if we're considering this surface, what is the value of y? The value of y is equals to 1. Okay, so that means we have the double integral 0 1 0 1 of y squared. Since y is 1, so it's going to be 1 squared, and this way z dz dx. Okay, and what next here? If we integrate respect to z, we're going to have 1 0 z to the power 2 over 2. The limits for z is 0, and we have dx. Okay, that means we have 1 0, and here we're going to have 1/2 dx. And if we integrate here, we're going to say 1. We're going to have 1/2 times x, then the limits for x from 0 to 1, and this is equal to 1/2. Okay, so we have 1/2 for the first surface, 1/2 for the second surface, and now we're going to the third surface. Okay, so as I said, the order doesn't matter, but now I'm going to this surface. Okay, so this is the blue, the green, blue. Okay, the surface which is opposite to this one. So I'm going to draw it right here. Okay, so for this surface, okay, as you can see, we have y is changing 0 to 1. Okay, x is not changing here, and we have z, okay, from 0 to 1. Okay, so this is surface number 3. I'm going to evaluate the double integral. Okay, so for surface number 3, with the double integral 0 to 1 for both y and z. Okay, then our vector function, we have x y I plus z y squared j plus z to the power 3 k. Okay, so for this surface, the outward normal, as you can see, which the outward normal which is perpendicular to the surface is going to be outward. Okay, and in the negative x direction. Okay, so now that means our normal is going to be negative I. Okay, and we are saying dz dy. Okay, so if we simplify, you're going to have 1 0 1 0. Okay, then if we multiply their component, we're going to have negative x y dz dx. Okay, then for this surface, we want to find the value of x. So for this surface, you can see this, it originates here, x is equal to 0. Okay, so that means we have the double integral of 1 0 1 0, and here we're going to have 0 dz dx. Okay, so if we integrate 0, we're going to have 0. Okay, so this is for surface number 3. Okay, not having anything, if you don't have anything here, that means we've got 1. But if we have 0, that means we're going to have 0. If you want to integrate anything, let's say if we say integrate respect to z, we're going to say 0z, and that is 0. So now we're going to the next surface, which is surface number 4. Okay, and for surface number 4, okay, so we said our vector field will still have x y I plus z y squared j plus z to the power 3 k. Okay, so now for the fourth surface, okay, so this is going to be surface number 4. Okay, let me draw it here. Okay, so now for surface number 4, as you can see, x is increasing from 0 to 1. Okay, so x is 0 1, and for this surface, which is z, it's increasing from 0 1. Okay, so what is going to be our double integral? Okay, so our double integral we're going to have for surface number 4, it's going to be double integral, I'm going to say dz dx 0 1 0 1, our vector field x y I plus z y squared j plus z to the power 3 k. Okay, so the outward normal for this surface, okay, so let's say there's liquid and it will flow in this direction. Okay, so this is the negative y direction. Okay, so y is growing as you go here, x is growing as you go here, and z is growing as you go upwards. So it's going to be negative j, and I'm going to say dy, sorry, it's this dx dz, okay, or dz dx. The limits are just the same, nothing will change. Okay, so we're going to have 1 0 1 0. Okay, I component, we only have the j component, I component 0, k component 0. So you're going to have negative z y squared dx dz. Okay, and now what is the value of y here? So at this plane originates here. Okay, this surface. Okay, y is 0, so we're going to have the double integral 1 0 1 0 for 0 dx dz, and we said we're going to get 0. Okay, now for the surface number 5. Okay, for surface number 5, now only left with two surfaces, the bottom, the top surface and the bottom surface. So for the bottom surface, I'm going to start with the bottom surface. Okay, so this was surface number 4. Okay, now for the surface number 5. Okay, surface number 5, the bottom, we have x here. Okay, from 0 to 1. Then we have y from 0 to 1. Okay, 0 to 1, this is y. And now we want to integrate our double integral 0 1 0 1. Okay, and now what is our vector field? xyi minus z y squared j plus z to the power 3 k. Okay, what is the outward normal? Okay, so we said if something want to flow, it will flow in a downward direction. Okay, so that is in this direction, the negative z direction. So that is our normal is going to negative k. Then we have dx dy or dy dx. Okay, so now I component 0, j component 0, so we're going to be left with double integral 0 1 0 1 of z to the power 3, since it's negative z to the power 3 dx dy. So what is the value of this, of z at this downward plane? Okay, as you can see, it's down. Z is 0, since the origin is here, z is 0. So we're going to give a double integral of 0 1 0 1. We're going to have 0 dx dy. So that means the total flux here is going to be 0. Okay, now we're just left with the top surface. Okay, so the top surface, this one, green, red, blue. Okay, so let me draw it here. Okay, so the top surface, if you draw the top surface, we're going to say we have y from 0 to 2, from 0 to 1, y is increasing. Then we have x. Okay, so x increasing from 0 to 1. Okay, so what is the flux? Surface number 6, we're going to say limits 0 1 0 1. Then we have our vector field xyi minus zy squared j plus z to the power 3 k. Okay, now what is the normal? Okay, so if something was to flow out, okay, it will flow on the top, going to this direction, which is perpendicular to this surface. It is the upward direction. Okay, so the normal is going to be k z direction, so that is equal to k, and we're going to say dx dy. Okay, so if we integrate here, first of all, by multiplying by k here, we're going to say 0 1 0 1 k, we have z to the power 3 dx dy. Okay, but you have to note something. In this plane, the up plane, or the upward surface, okay, the top surface or top plane, okay, z is not equal to 0, because the originates here, z is equals to 1. So that means we have the double integral 0 1 0 1 for 1 dx dy. Okay, and if we integrate back to x, we're going to have 1 0 x 0 1 dy, and that is equal to the integral of 1 dy, and that is equal to y 1 to 0, and we have 1. Okay, so we've evaluated each and every flux for each. We've evaluated flux for each surface. So what is going to be the total flux? Okay, so the total flux, we're going to say surface number 1, surface number 2, plus up to surface number 6. Okay, then for surface number 1 we get half, for surface number 2 we get half, third surface we have 0, fourth surface we have 0, and for the fifth surface also we have 0, and for the last surface we have 1, and this is equal to 2. Okay, and when we calculated the total flux here using divergence theorem, we also have 2. So what is our conclusion now? Okay, so now what can we say? Now you can say, as you can see, we verified the divergence theorem. Okay, since the total flux which calculated on each and every phase was equal to the flux we calculated when we used the divergence theorem, we can say that the divergence, we verified the divergence theorem. Okay, so you should be just be very careful with the coordinates, whether x is 0, x is 1, y is 0, y is 1. Okay, thank you for watching.